In 1938, in the dark heart of Hitler's Germany, a chemist discovered, without immediately realizing it, the key to the most powerful weapon in history. And yet the atomic bomb would not be built by Germany, but by its enemies. This story is not just about physics. It's about how a discovery ends up being used not by the country that made it, but by its enemies. Not by chance, but through pride, hatred, and a series of catastrophic choices. It's the story of one of the greatest ironies of the 20th century. It's December 1938 in Berlin. The cold has settled on the streets, and in a laboratory at the Kaiser Wilhelm Institute for Chemistry, researchers Otto Hahn and Fritz Strassmann are repeating an experiment that's giving them a hard time. They are bombarding uranium with slow neutrons. They expect the uranium to absorb the neutrons and thus produce elements heavier than uranium. That's what the logic of the time predicted. But experimental analyses show something unexpected. Barium is obtained, an element twice as light as uranium. Otto Hahn, a meticulous chemist, is convinced that it's contamination. He repeats the experiment repeatedly. Barium appears every time. This is the moment to understand who the protagonists of our story were. Otto Hahn, born in 1879, was a pioneer of radiochemistry, already famous for discovering some isotopes. Fritz Strassmann, 23 years younger, was a talented chemist who refused to join the Nazi Party, which is why his career had been blocked. They formed an efficient team of experimenters. Whenever they had trouble understanding the theory, as was the case now, they would turn to a friend, a liberal physicist, Lise Meitner. An Austrian physicist of Jewish origin, Lise Meitner had worked side by side with Otto Hahn for more than 30 years. She was the brains behind the theory behind their experiments, the one who asked the fundamental questions. However, after the Anschluss, her position had become unbearable in Germany. In 1938, Meitner had fled Germany clandestinely, helped by Dutch colleagues. Now she was in exile in Stockholm, and her correspondence with Otto Hahn continued cautiously by letter on December 19, 1938. Frustrated by the still inexplicable results of his experiment, Otto Hahn writes desperately to Lise Meitner. Maybe you could suggest a theoretical explanation. How did the barium get there? Lise Meitner receives the letter in Sweden, right in the middle of the Christmas holiday. She reads it together with her nephew, the physicist Otto Frisch, who is also a refugee from Austria. They talk while walking in the snow. She walks, he is on skis. And then, in a moment of inspiration, the two imagine the atomic nucleus not as a solid ball, but as a drop of water. A neutron that hits this drop can deform it until it breaks into two smaller fragments. And the mathematical calculations made by Lise Meitner fit perfectly with the experiment. In their laboratory, Otto Hahn and Fritz Strassmann had just caused, without realizing it, the first experimentally observed induced nuclear fission. The fission fragments are actually barium and krypton nuclei, and its splitting releases a colossal amount of energy, millions of times greater than any chemical reaction. Otto Frisch, the nephew of Lise Meitner, found the right word, fission. Inspired by the biology term cell division, after a discussion with the biologist William Arnold. The theoretical description appears in the journal Nature in February 1939. Meanwhile, Hahn and Strassmann had published the experimental result at the beginning of January 1939, without mentioning Lise Meitner. Not out of malice, but in a political context in which her name, as the Jewish woman who had fled Nazi Germany, had become impossible to officially associate with a paper published in Germany. Another bitter irony. Why was this result so explosive? Because it wasn't just a laboratory curiosity. Each fission produced, besides fragments, additional neutrons. If those neutrons hit other uranium nuclei and caused new fissions, a chain reaction could arise. A cascade that, if left unchecked, could devastate entire cities. In January 1939, the moment we're talking about here, Europe was on the brink of disaster. Hitler had annexed Austria and torn the Sudetenland from Czechoslovakia. War seemed inevitable. And now, right in Germany, a mechanism had been discovered that was capable of generating unimaginable destructive power. The news of the discovery of uranium fission spreads like lightning. Otto Frisch immediately tells Niels Bohr, the Danish master of quantum physics, who in mid-January 1939 was embarking for America. On the ship, Bohr talks with Leon Rosenfeld and after reaching New York shares the information with his Princeton colleagues. Within a few days, American labs replicate the experiment. In just a few months, the idea for the most powerful bomb in the world had already left Germany and reached its enemies. Hitler didn't even realize what had slipped out of his hands. In America, Enrico Fermi, the Italian refugee who had won the Nobel Prize for Physics and fled with his family because of racial laws, is also looking at the results. A collective fear is born, but also a silent mobilization. In the spring of 1939, a Hungarian exile in America, Leo Szilard, immediately realizes the danger. Szilard had the general idea of the chain reaction as early as 1934, but he had kept it more or less secret because of the danger. He had done so for fear of military escalation. Now he fears that Nazi Germany will not hesitate. Together with physicists Eugen Wigner and Edward Teller, Szilard visits Albert Einstein, who is at a vacation house on Long Island. Einstein, although a convinced pacifist, understands the implications. Then Einstein signs the famous letter addressed to President Roosevelt in August 1939, warning that Germany could build atomic bombs and urging the United States to start its own research. Einstein's letter did not have an immediate effect. At first, Washington reacted slowly. A uranium committee was established, but only in 1942 after Pearl Harbor, and after the fear of a German nuclear program became acute. The Americans launched the Manhattan Project only then. The project to build the first atomic bombs was a huge industrial effort, coordinated by General Leslie Groves and led scientifically by Robert Oppenheimer. The project brought together thousands of scientists, many of them European refugees. Fermi, Wigner, Szilard, Taylor, Bohr himself, and many other European scientists, including numerous Jewish researchers who fled from Hitler's persecution. They would form the brains of the project that was to defeat the last Axis power, Japan. Exactly the minds that Nazism had driven away or would have destroyed if they had stayed in Germany. The first challenge of the Manhattan Project, building the first atomic bombs, was that natural uranium simply isn't good for a bomb. It contains mostly uranium-238, and the isotope that can easily sustain a chain reaction, uranium-235, is present in only a very small proportion. So the Americans had to do something extremely difficult, increase the concentration of uranium-235. But uranium-235 and uranium-238 are almost chemically identical. They can't be separated with a sieve, an ordinary filter, or a simple chemical reaction. The difference between them is only one of mass. One is slightly lighter than the other, and the Manhattan Project turned this tiny difference into a huge industry. In Oak Ridge, Tennessee, the Americans built secret cities and giant factories. They used several methods in parallel: electromagnetic separation, gaseous diffusion, and thermal diffusion. It was as if they were trying to separate two types of almost identical sand, grain by grain, repeating the process millions and millions of times. Uranium concentration increased slightly at each stage. 235 until the material became enriched enough to build the Hiroshima bomb. The uranium bomb, called Little Boy, was simpler in concept than the second atomic bomb, the one with plutonium. Inside, two masses of enriched uranium, each kept separately below the critical threshold, were suddenly brought together. At that moment, the configuration became critical, neutrons began to trigger a chain reaction, and the energy released became catastrophic. Precisely because this design seemed more straightforward, the Americans didn't even test the uranium bomb beforehand. The Trinity test in July 1945 was for the second atomic bomb, the plutonium one, which was much more difficult and of the implosion type. For the first bomb, Little Boy, the uranium bomb, the main challenge wasn't so much the shape of the bomb, but producing the material. Obtaining a sufficient amount of enriched uranium-235 after years of industrial work, money, electricity, ore, secret facilities, and tens of thousands of people who often worked without knowing what they were contributing to. And yet, what was Germany doing while America was building the first nuclear bomb? Shortly after the discovery of fission, in April 1939, the German chemist Paul Hartek wrote to the Nazi Minister of War that nuclear fission could lead to an explosive of unimaginable power. Thus, the Uranverein, the Uranium Club, was born in Germany. A lesser-known episode takes place in 1941 in Bucharest. Just a few days after the Romanian physicist Horia Hulubei became the rector of the University of Bucharest, Otto Hahn, the man who discovered fission, visited Romania. In a conversation held in the modest atomic physics laboratory in Bucharest, Hahn says something disturbing. Nuclear energy could be used in the not-too-distant future, either for the survival of humanity or for its self-destruction. But he also believed that the technological difficulties of a nuclear weapon are so great that the bomb would not be able to determine the outcome of the ongoing war. In Germany, Werner Heisenberg enters the scene, one of the brightest minds of the century, Nobel laureate, the father of the uncertainty principle. Unlike many of his colleagues, Heisenberg had remained in Germany, convinced that he could protect German science from within. It is said that Heisenberg, a man of formidable intelligence, nevertheless made a serious technical error when he did his initial calculations. Some reports say that he and his team miscalculated the amount of fissile material needed for a bomb. He is believed to have thought that several tons of purified uranium were needed, when in fact just a few dozen kilograms would have been enough. I'm not sure if this story is entirely true. I got it from the book Heisenberg and the Nazi Atomic Bomb Project. It is mentioned there that on the evening of August 6, 1945, when he first learned about the bombing of Hiroshima, Heisenberg is said to have reacted by saying that he didn't believe it was actually a real nuclear bomb, because he couldn't imagine that the Americans had managed to produce the 2 tons of uranium-235 that he considered necessary. On the other hand, I found this article. The article says that at a meeting on June 4, 1942, Heisenberg is said to have told Field Marshal Ernhard Milch that a nuclear bomb would be as big as a pineapple. Which is almost true if we're only talking about the amount of uranium-235. The truth could lie somewhere in between. Heisenberg couldn't accurately estimate the amount of uranium. This couldn't convince them that an atomic bomb was an achievable goal during the war and would have shifted their attention to a nuclear reactor, a source of energy, not a weapon. Moreover, Germany never treated the nuclear project as an absolute priority. Huge resources were channeled into V-2 rocket tanks and airplanes, not into a weapon considered too distant and too uncertain. And the coordination was also chaotic. Several rival groups, that of Heisenberg, a Nobel laureate and the central figure of German physics, and that of Kurt Deibner, directly supported by the army, worked in parallel, without a unified strategy and without massive industrial support. The exact opposite of the monolithic Manhattan Project. To this was added another major technical error. To slow down the neutrons, the Germans needed a moderator. They chose heavy water, produced at Vemork in occupied Norway. Graphite, much easier to obtain, was rejected by physicist Walter Bothe after incorrect measurements and unreliable analyses regarding its purity. Thus the project became dependent on a single vulnerable source, which Norwegian commandos and the Allies sabotaged in 1943 and 1944, sinking the transports and burying for good the chance of a functional reactor. The story is admirably told in the film The Heroes of Telemark. When Heisenberg met with Albert Speer, the Minister of Armaments, in June 1942, he presented his conclusions. An atomic bomb required a lot of uranium and an industrial effort that exceeded Germany's wartime capacity. Speer, facing enormous demands at the front, decided to fund only small-scale research. Heisenberg did not lie, although some say he consciously sabotaged the project. I believe he presented an erroneous assessment, probably also influenced by moral qualms. Overestimating the difficulty and the regime's lack of understanding did the rest. On top of that, the mass departure of scientists of Jewish origin, the ultimate irony, drained Germany of the minds that could have solved the problems. People like Leo Szilard, who had intuited the chain reaction, Eugen Wigner, who would go on to help design nuclear reactors, and Edward Teller, who would later work on the hydrogen bomb, all ended up on the opposing side. Without them, the German scientific ecosystem was wounded, isolated, and lacking that creative effervescence which had fueled the laboratories in the 1920s and 1930s. In July 1945 in the New Mexico desert, the Manhattan Project detonated the first atomic bomb in history. A few weeks later, Hiroshima and Nagasaki were almost wiped off the face of the earth, and the Second World War came to an end. The irony could not have been greater. The discovery of nuclear fission, made in the heart of the Third Reich, led to the weapon that struck the last major Axis power still fighting, Japan. Hitler had dreamed of a miracle weapon that would turn the tide of the war, but he was the one who drove away and marginalized exactly the kind of people capable of building it. And the fear of Nazi Germany, amplified by Einstein's letter and the nightmare of an atomic bomb in Hitler's hands, was the driving force that made America invest $2 billion and mobilize 130,000 people to be the first to reach the finish line. In the end, the story of nuclear fission is not just a lesson about energy and neutrons. It's a historical parable about how ideology and hatred can turn the greatest advantage into a strategic defeat. Nazi Germany discovered the key to fission in a laboratory in Berlin, but suffocated by anti-Semitism, pride, and lack of vision, it lost it along the way. And the world has never been the same since. If you enjoyed today's story, where I combined physics with history, please write in the comments what other topics you think should be covered. I want to thank those who have subscribed on Patreon, where they can receive video answers to science questions directly on WhatsApp from me. Until next time, I am Christian Prasura. I wish you all the best. Goodbye.